Okay, well, let's look at the pseudocode for one of the specific RK methods, and we'll look at the midpoint method. It's a pretty simple pseudocode. The inputs, that's just information that you need to know. You need to know A and B, your starting point and ending point. So your initial value, your initial condition A, that's really the same as your initial X. These are the same. Frequently, that's going to be the number 0. And then in our examples earlier, B was 3. So you could go in 2 steps. If n were 2, you'd go 2 steps from 0 to 1, 1.5, and then to 3. If n were 3, and if n were 3, and B were 3, that means that your step sizes would be 1. It's going to take 3 equal-sized steps to go from 0 to 3. 1, 2, then 3. And actually, that's the first line of the pseudocode. You'll also need to know your initial value for your initial condition y, 0. So the function, you have an xy pair as your initial value. The initial value x naught is going to be a, and then y naught would be the y value corresponding to that. Okay, the very first thing we do is compute the step size. We take b minus a, and in our example, if we did 3 minus 1, 3 minus 0, that would be 3 divided, this assumes a 2-step. I'm going to change that to n. We might change it to any number of steps. It doesn't make it any more difficult. So the step size, you take the b minus a, the width, and you divide it by n. X, as we already said, this is just the initial X. This is the initial Y, the initial conditions. And we jump into a loop. So for the n steps that we have to take, we're starting at, you could think of it as time 0 and taking 1, 2, 3 n steps to get to where we need to be, which would be lowercase b. We have to compute 2 interim variables, didn't know what to call them, x1 half, or y1 half and x1 half. Just call them whatever you want to. They represent going halfway. They're temporary variables, only used in the next line and nowhere else. So we've got y1 half equal to y, which was y naught, remember, plus 1 half h f of xy. All right, x is simply going to be x plus 1 half of h. So we're kind of jumping out halfway, and we're going to get a slope there. So y is equal to y plus h times f of x1 half, y1 half. And that's the only reason we got these 2 local variables. You can call them u and v, w and z, it doesn't matter. And then as usual, I've got this solution, just an array that keeps all of the y values so you can plot them at the end. And let's see, x has to be incremented by h, and then go back up to the loop. So this is the end of the 4k loop. And you've got this probably in your notes, but one way in Mathematica of displaying some points is using discrete plot. And solution and k goes from 0 to n. But feel free to plot it in any other way. See, if n were only a 3, we've got the initial value, second value, and a third value. So it would simply be 3 dots. If you want to use that graphics function that I talked about in an earlier video, and the line, capital L-I-N-E function, you can do this if you'd like. And that should help you along with your programming assignment. And I think, let's see, that is the end of Runge-Kutta Methods.